In this problem, we're calculating electric flux through a flat surface. The flat surface will be in the xy plane. It extends from x equals 0 to w and from y equals 0 to h. Any area vector that I represent that area with is going to point either in the k hat direction or the negative k hat direction. So an area vector is going to be some magnitude times k hat. Doesn't matter which one we pick, I'm going to pick positive k hat. Now the definition of electric flux is the integral of the electric field dotted with that area vector. So if we perform that dot product, we see that we're only going to pick up the k hat component of the electric field. So let's just write out that dot product. We still haven't decided whether we actually have to integrate or not. But we need to write this out and look at the expression, and then we decide whether we're going to integrate. So I'm just going to have in the integral the cx dA. Now, as we're moving through that area in the xy plane, we can see that x is changing. So the expression in the integral is actually changing. So we do need to integrate, which means now we need to divide this area into little elements. And we have a few choices. We could divide them into vertical strips, horizontal strips, or little tiny rectangles. Now, the way you decide which way to divide that area is you look and see that the variable x is changing, which means the electric field is getting stronger as I move over to the right. It's not changing though as I move up and down. So if I make my dA a vertical strip, the electric field will be constant in that little strip. So my thickness, dx, will represent the width of the strip. The area of this, dA, is then equal to h times dx. So if I put that into my integral, I have c times x times h dx. And the limits of integration on x are from 0 to w. The c and the h are constant. X dx, the integral is x squared over 2, evaluated from 0 to w, which just gives chw squared over 2. And that's the electric flux through that area.